For this presentation, we will apply the fundamental theorem of Galois theory to study the roots of a polynomial. It's important to note that we are going to be considering polynomials which are irreducible over Q. Referring to the fundamental theorem, we know that it tells us that the subfields of the field generated by the roots of a polynomial correspond to the subgroups of the Galois group of some polynomial p of x. So we want to figure out what it tells us about the roots of a polynomial. So if we consider a polynomial of degree 2, which is irreducible over Q, I'm going to use the example of the polynomial, the quadratic x squared minus 2. We've looked at one similar to this throughout Unit 4. So we want to recall what we know about the splitting field. Since x squared minus 2 equals 0, we know x squared equals 2, and x must be both the plus and opposite versions, plus and minus of the square root of 2. So our extension field must be q of root 2. So I borrowed this graphic actually from another friend who was trying to help explain this to me a little bit. If we think about our field of q and containing elements like a and b, some rational numbers, right, we need to extend that field to include values that in this case would include root 2. So in that extension field, we would see elements like a plus, that should say a plus b square roots of 2 and a minus b square roots of 2. So I missed my b in there. I'll use a different color to pencil those in. So we know the splitting field has degree 2, and as a result, the Galois group is then isomorphic to Z2. The only subgroups of Z2 would be the identity and Z2 itself. The subfields of EP fixed by the identity would be EP itself. The subfield of EP fixed by Z2 must be Q. So this has to give us the following correspondence. The identity maps to EP and Z2 maps to Q. So what does this correspondence tell us about the roots of these polynomials? Well, if sigma is the only non-trivial Q automorphism of EP, we know that sigma has to have order 2 and can be written as the conjugation of a square root. So this implies that we can write the roots of p of x by performing basic field operations involving q and a single square root. In this particular case, it would be root 2. If we consider another example, I'm going to continue to use a quadratic polynomial function as examples. P of x, right, we want it to be reducible over q. And we could check, and I didn't mention this with the first example of x squared minus 2, that previous polynomial, that we could, use other concepts we've used throughout this course, like the rational roots theorem, for example, to prove and to show is irreducible over q. But we've already talked about that, so we'll skip that for now in this presentation. We know it has degree 2 since it's quadratic, and so we could use the quadratic formula to take a look at the zeros or the roots of the polynomial. So we do that as quick as possible. We get, as I'm plugging through that quadratic formula, we would see x would be 5 plus or minus root 7 over 2. And so our extension field right, again, that idea of we know our roots contained in our rational numbers q, but we need to extend that field, in this case, to q root 7. And so the Galois group of p of x contains e and the conjugation, which we're going to define that as sigma, such that q root 7 maps to q root 7. Oh my goodness. There we go. And a plus b squared 7 goes to its conjugate, a minus b root 7. So again, to include the roots of p of x, we need an extension field as defined to talk about those roots of the polynomial. So by definition, we know E fixes the whole field, Q of root 7. And sigma fixes only the rational numbers because, I should probably note that, sigma of A plus B root 7 sends it back to A plus B root 7. So we want to find some A and B such that A plus B root 7 will send it to A minus B root 7, the conjugation. And so through some simple algebra in here, right, if we subtract A to both sides and then add B root 7 to both sides to get 2 times B root 7 equals 0, then we know B has to equal 0. Well, if B equals 0, this means that A plus B root 7 or A minus B root 7 must become A plus or minus 0 root 7 or just A, which we know would be in our rational numbers in our original field Q. So we must have the following correspondence. Identities maps to Q root 7, right? It sends every element back to itself. And Z2 maps to our field of Q.